Hi. So where are we in the course? So far, all we really have done is we examined the relationship between space and time. So in physics, in physics, we study motion of things. We study how things interact. And that motion, those interactions, take place on a stage. That stage is space and time. So far, what we did is we re-examined the properties of that stage. We've done absolutely nothing about stuff on that stage. We didn't even do basic things like define kinematics on that stage. So if you would like to learn more about that, you can watch extra videos, optional videos that I put in the same lecture section with this one. The reason there are so many optional videos is that I'm trying to make the course more palatable to a wider audience. And therefore, I'm trying to refilm things in a way that's uh, even simpler and shorter and more accessible to students of wide ranges of preparation. However, there are older videos that are a little bit more in depth, and I will leave them for those students who would like to learn those more in depth points. So in that optional video, I discussed how to do kinematics. For now, our goal is to discuss um, energy and momentum in special relativity. The properties of the stage, the properties of the relationship between space and time affects what goes on that stage. It affects the dynamics of particles. It also affects our understanding of big things like energy, for example. So in order to motivate our new understanding of energy, which is going to be useful for solving problems, and it will also be useful when we start on the quantum mechanics module, it's instructive to look at a following example. Let's look at collision of two particles and examine momentum conservation. It's not obvious why we're doing that, but it will become obvious. So what I'm going to do is I'm going to let's examine so what I have is I have some particle of mass m1 moving to the right with velocity u1 initial, and a particle of mass m2 moving to the left towards it on a collision course with velocity u1 final, and they collide. For simplicity, let's say the particles retain their identities, and in particular, they retain their masses. So after the collision, we still have M1, but it's now moving with U1 final, and M2 moving with U2 final. However, the same analysis holds if the products are different than the reactants. For example, they exchange masses or something like that. So this is before, and this is after. Sorry, I caught my typo. This is supposed to be initial. Okay, the two initial velocities and then the two final velocities. Standard scenario. Okay, now this is correct. I said we're going to focus on momentum. First of all, where does the concept of momentum come from? This MV business, or MU, I'm using U for velocities. Where does it come from? Why do we even talk about it? The reason we talk about this quantity, the reason it even has a name, is because that quantity is conserved. So it's special. The reason we talk about energy, for example, mechanical energy, is because it's a quantity that is conserved as time unfolds. For example, in collisions, before and after. Things that are conserved, they're special, so they get a special name. Recall what we want the law of recall that we want the law of conservation of momentum to be invariant. The law to be invariant. And that means that if momentum is conserved, then it has to be deemed conserved in any other frame. Before relativity, the way we switched from frame to frame is by means of a Galilean transformation. You had that exercise in homework 1. I dearly, sincerely, very seriously hope that you actually looked at solutions. Otherwise, you're going to have a difficult time now. So we switched from frame to frame by means of a Galilean velocity transformation. But now we already know that it's not a correct way to transform between frames. Before relativity, it was assumed that principle of relativity is the same as finding invariance under Galilean transformation. Now we know that principle of relativity means that a law is Lorentz invariant, not Galilean invariant. Conservation of momentum is a law. It's a relationship. Law is a relationship. Therefore, what we really want is we want such a definition of momentum that remains such a definition of momentum that if the total momentum of particles is conserved in one frame, then when we perform the Lorentz transformation, when we boost ourselves to another frame, the form of the relationship between initial and final momenta stays the same. If that's true, then we found a good definition of momentum that works even in the relativistic stage. I discussed the new stage. Well, new stage requires new quantities. It requires redefining momentum. It requires redefining energy. And that's what I would like to do. But to begin with, let's check if the classical momentum is Lorentz invariant, the MU, the boring classical vanilla definition of momentum that you learn in Phys 1. Okay. So let's say in one frame, it's true that the sum of products of MUs, the net sum of products of M times U is the same before and after collision. Would it still be true that the form of that relationship remains the same when we boost ourselves to another frame by means of a Galilean transformation? That's initial equals so I'm saying let's guess that even in relativity, momentum is still given by this expression. In other words, this kind of quantity before equals that quantity after. Well, if it's a good quantity, if it's a good definition of momentum, then when I boost into another frame, this same relationship holds true with just different velocities, because velocities change from frame to frame. Okay, so let's say this is true, then so I'm not going to use primes because that's too many subscripts. I'm going to use tildes. So this is velocity in new. So this is frame S, this is frame S prime. Yeah, because you're used to me using S and S prime. This is what it means to say that the form is preserved. The form of the relationship looks the same. There are no new terms like that involve u squareds, tangents of u, new types of animals don't appear. It's the same animals, just with different u's because velocities transform. So we would say that the form, this is what it means to say that the form is preserved. So that's the question. Is that, would that be true? Is that true? Let's check. So let's check that. And if that's true, then mu is still a good definition of moment. So we need to start from frame S, start with this expression, and perform the relativistic velocity transformation from S to S prime. We know how velocities transform. We know the relativistic velocity transformation formulas. So starting with the supposed momentum conservation in the unprimed frame and transforming to the prime frame, we would get the following relationship. And actually, it would be a really good idea if you pause the video and do the transformation yourself. So we need to transform each one of these guys right here into S prime. So it's the usual scenario, right? So you have frame S, then you have a frame S prime, and it's moving with velocity v relative to frame S. So the transformation would involve the v. And you know how to do that. So what we would get is we would get the following. Sorry, just barely fit on the page, barely. Beauty of writing is not my forte. Let me clean it up a little bit, okay? 1 second. Okay, that's the best I could do. And so, do we get this? Does what I just wrote look like this? No, it doesn't. Why? What about this new expression that makes it not look like the same form just in a new frame? Why? Because of these denominators. If there were no denominators, then it would be the same form. And the reason why it would be the same form is hopefully you understand why through doing the homework. We actually did this thing in one of the earlier lectures. The products of m times u tildes would become exactly what we want. And then there would be terms like m1 plus m2v on the left and m1 plus m2v on the right, and those things would cancel, and boom, we would get this kind of thing that we want. It's the denominators that screw things up. So because of these denominators, we see that if the sum of products of m times u's was conserved in one frame, that sum of products of m times u tildes is generally not conserved in another frame. So m times u has to be thrown away. It doesn't work anymore. On the new stage, it needs to be upgraded. It doesn't work the way it did on the old stage. You see, stage matters. I'm just going to state it to you. Think of this as a divine inspiration. One could possibly arrive at this divine inspiration that I'm about to state to you by looking at this thing, looking how it failed, and thinking up, making a guess of the new form of momentum that does work. So it would be more complicated in the first frame, but then when we do perform the velocity transformation, we retain the form. Think of this as a divine inspiration or a dream or something like that. So let's try the following. P, the relativistic momentum, equals gamma times u. Now you see gamma contains the u in it. So if we are going to be dealing with different u's, there's u1 initial, u2 initial, u1 final, u2 final. Each one would have its own gamma. So to remind ourselves what u goes inside the gamma, I'm going to put a little subscript u. In this case, it's unnecessary because here I'm only dealing with one u, but now we're going to be dealing with 4 u's, and so there will be 4 gamma factors. And to keep track of what gamma factor we're using, I'm going to have to keep using those subscripts. I hope this is clear. So I claim that this works. I claim that this works. So let's say that P net initial is now given by the following more ugly expression. And that it equals to actually, let me write it like this. So what I wanted to say is I wanted to say the following. So let's say we have a conservation of the total of this new type of quantity. And let's say in frame S, this thing was conserved. I'm not proving it. I'm saying let's say that it was, and let's check if it will be deemed to also hold in a new frame when we transform to a new frame. Notice I'm not proving conservation of momentum anywhere here. That's a separate ball game. I'm just testing whether a particular definition of momentum is Lorentz invariant. That's what I'm doing. I'm not proving momentum conservation. So with this more cumbersome quantity, we would do the same thing. As we boost from frame S to frame S prime, all these puppies acquire this ugly form of that, like this fraction type of thing. However, what would really help us is there's an identity. There is an identity that would help us. It would be helpful for cleaning things up. Now, to some of you, this class is like going to a dentist 4 times a week for 10 weeks. I know, I understand. But some really love math and they really want to know more. So this kind of thing is proved in your textbook in one of the exercises. So if you want, you can do that exercise. I think it's exercise 69, something like that. Just 1 second. So there is this identity. Right, so if you have three velocities involved, u prime, and v, and gamma mentions a u inside, there's this interesting relationship between gamma that corresponds to each velocity. To each velocity, there corresponds a gamma. And there's this interesting relationship. So using the relativistic velocity transformations and this identity, so when we use this identity and the velocity transformation, after some algebra, we would find the following. It's going to be a mouthful. This is what we would find. Is the form preserved? So we started with this. So we started with this. We ended with this. Do the two relationships have the same form? No, they don't. They only will have the same form if, in addition to this being conserved, that this quantity is also conserved. So we could call this, the first pair of terms we could call the p tilde net. And it's only conserved if the other pair of terms are also conserved. So p tilde net equals m1 gamma u1 is indeed conserved in the new frame. That's why I put the tilde. Only if, let me make it like that, only if so this suggests how we need to change the statement of conservation. New conservation claim. One, and two. We can't just start with the total momentum conserved, right? So this is P total initial, this is P total final. Something else has to be conserved simultaneously. So this exercise has shown to us how to upgrade the conservation statement that has to be true in order for everything to be self-consistent. Then, upon boosting into S prime, we would also get I'm gonna pause and just write things out because you don't need to watch me writing that. So we would get this. I noticed when I was rewriting this, I noticed that I had a mistake here. This said M2, so I fixed it. So it says M1. So in other words, let's say we start with these two things, and then I take the expression one and I boost into the new frame. When I boost into the new frame, I would get something like this, some sort of a expression like this one. And I see that 1 tilde is true only if 2 tilde is also true. And so therefore I see that there's a pair of quantities that has to be assumed to be conserved simultaneously in one frame. There's a pair of quantities. One is what we define to be the total momentum, and then there's something else. What's the other quantity that's conserved in a collision? It's energy. So could that second mysterious quantity be the relativistic definition of energy? Well, this doesn't have the right units. It doesn't have the right units. It doesn't have the right units. But to make the right units, we have to multiply by velocity squared. But the quantity gamma m c squared does have the right units. So what's the upshot of this? What have we found? We tried to conserve momentum. We found that on the new stage, on the relativistic stage, with relativistic properties of space and time, the old definition of momentum doesn't work. So we had to redefine it. And in the process, we found that momentum cannot be conserved independently. It has to drag along with it the energy conservation. Now, in classical physics, if you have a collision, let's say you have an elastic collision, you have conservation of momentum and you have conservation of kinetic energy. So energy, kinetic energy can only be conserved if the system is isolated, and if the system is isolated, momentum is conserved. If it's an inelastic collision, kinetic energy doesn't have to be conserved. It can be transferred into thermal energy, into heat. And there's an overarching super belief, super law that total energy, kinetic plus internal, has to be conserved. But that was a statement, that was a separate statement. As far as the momentum is conserved, as far as the momentum is concerned in classical physics, there needs not to be any mention of energy. In order for the momentum to be conserved, all that we have to have is that the system is isolated. It doesn't experience any forces. No mention of energy whatsoever. When you study momentum in physics 1, when you study momentum conservation, you do that before you even talk about energy. As long as there are no external forces, momentum is conserved. In relativity, that's no longer true. Momentum is conserved. Momentum conservation must also come in package with energy conservation. The two things are not conserved independently anymore, which probably suggests to you that momentum and energy are kind of part of one super thing. what are the other examples that we see in relativity where things that we thought of as separate become part of one object? Oh, space and time. They become part of space-time. Turns out, and I'm not going to show that, momentum and energy are also part of a super package. Some books call it momenergy. So you can see that this simultaneous conservation of momentum and energy is necessitated by the intermixing between space and time. So anyway, let me summarize. In relativity, P equals gamma mu, and E equals gamma mc squared. Both quantities have to be conserved together. In non-relativistic physics, conservation of momentum says absolutely nothing about energy. We do believe that energy is conserved, the total energy is conserved, it's true. And if collision is elastic, then in order for it to, for the mechanical energy to be conserved, momentum has to be conserved. But when we talk about momentum, we don't have to involve any energy argument. In relativity, that's no longer true. The two are interweaved. And I will leave this by just telling you that the reason the two are interweaved is because space and time are interweaved. So the next thing to do is now to start using these things. What I tried to do is I tried to give you the simplest motivation I could think of for these new definitions of momentum and energy. Next thing to do is to try to digest what this means. This has a very deep implication. And then just when we start the quantum mechanics module, we will use conservation of both momentum and energy for certain reactions involving photons. And on the homework, you will also get to practice using this momentum and energy conservation laws. You know, conservation, momentum, and energy given in this form, you will practice that. And maybe I will also do an example. So what I did today was not a derivation. It is not a derivation. I'm not deriving this. This was not a rigorous derivation to begin with. This is a motivation. We started by realizing that we're working on a different stage. And we said, well, what kind of implications does working on this new stage have on dynamics? We could talk about laws of motion. We could talk about how Newton's second law changes. We didn't. If I have time, maybe I'll say a few words about that too. But I focused on things that are the juiciest things that are often encountered in relativity, namely the connection between mass and energy. So we had to chat about things like energy and momentum. And we asked, well, what does the new stage, what kind of implications the new stage have on energy and momentum, or momentum, start with momentum. And we came to this thing that I just wrote down at the end. I try to be really clear. Sorry if this is too mathy for you. Again, it's not me against you. I'm trying to do my best, the best I can to help you deal with the subject. Okay? All right. Thank you. See you later.